All right, let's dive right into this explainer and uncover something truly fascinating about the ground beneath our feet. When we stand on a beach or look out over a cliff edge, it is so easy to get completely mesmerized by the crashing waves and the howling wind. But what if I told you that the hidden properties of the rock itself actually dictate the shape, the erosion rates, and ultimately the fate of our coastlines?
See, we usually assume the ocean is doing all the heavy lifting, right? We watch a coastline recede, and we immediately blame a violent storm. But honestly, that's only half the story. The real master architect here is the geology, right there on the coast. The physical and chemical characteristics of those rocks are secretly determining exactly how and where the ocean is actually allowed to do its work.
So, here is our roadmap for today. First, we'll look at the architects of the coast. Second, lithology, weak versus strong. Third, structure, fractures and folds. Fourth, structure, angle of dip. And finally, we'll pull it all together with the sediment cell system.
Okay, Section 1, the architects of the coast. Let's establish the two grand pillars of geology that really control everything we're talking about today. Now, this is absolutely crucial. You can never conflate these two terms. Lithology is the rock type itself. We're talking about the physical and chemical characteristics of the rock on a microscale. It's literally what you'd see if you put a tiny specimen under a microscope. Structure, on the other hand, well, that's macroscale. It refers to the large-scale characteristics of the coastline, looking at how massive blocks of rock are arranged, folded, and fractured. A good way to think about it is lithology is the specific ingredients you mix together to bake a single brick, whereas structure is exactly how you stack those bricks to build a massive wall. Moving on to Section 2, lithology, weak versus strong. Let's see exactly how a rock's microscopic chemistry determines its survival against the sea. Just picture the crumbling glacial till in East Yorkshire for a second. It constantly experiences violent rotational slumping and heavy mass movement that literally tears the cliff apart. Now, contrast that with the towering, impenetrable igneous basalt columns at Reynisfara Beach in Iceland, which stand there almost completely unbothered by the waves. That night and day difference? That is entirely due to their lithology. Let's break down why that happens. Rocks with a weak lithology, things like clay or certain sandstones, they offer very little resistance to weathering and erosion. Clay, for instance, is just made of extremely fine particles of decomposed rock that just sort of stick together. Sandstone grains are bound by natural cements, like silica or calcium carbonate. But if that cementation is weak, the rock falls apart super easily. It's kind of like taking a handful of glass marbles and trying to stick them together with just a tiny bit of weak sticky tack. Those extremely weak bonds are easily broken by the ocean. But conversely, if you zoom in on a microscopic view of basalt, it reveals highly resistant, dense, interlocking crystals. There is absolutely no weak sticky tack holding this together. These crystals are tightly locked into one another like a massive, complex puzzle, and that microscopic chemistry makes it incredibly tough, giving it a strong lithology that fiercely resists erosion. All right, Section 3, structure, fractures, and folds. Because the truth is, even the strongest rocks in the world can be brought down when they're warped and broken by powerful tectonic forces. Think about the dramatic folds at Stairhole in Dorset. This is geological structure in action. These layers of rock have been bent and distorted by unimaginable tectonic power from deep within the earth. And when rocks are folded and fractured on this massive scale, they present profound weaknesses that the sea is practically begging to exploit. Specifically, structure introduces joints and faults into the coastline. Now, joints are simply naturally occurring cracks where there hasn't been any movement. Faults, however, are massive fractures where rocks have actively moved in opposite directions along a fault plane. Whether a rock is well-jointed or deeply faulted, the ocean's hydraulic action is going to ruthlessly target those structural weaknesses. The immense water pressure of crashing waves violently forces trapped air and water into these cracks, basically acting like microexplosives that blast the fissures wider, and eventually they just collapse into deep coastal caves. Next up, Section 4, structure, angle of dip. The specific angle at which sedimentary bedding planes sit completely changes the stability of a cliff. When the bedding planes are uniform and perfectly horizontal, they naturally produce those iconic, steep-sided coastal cliffs you always see in postcards. Because the layers are flat, gravity is just pulling straight down on a really solid, stacked foundation. However, if those structural layers dip towards the sea, the situation gets incredibly dangerous. A seaward dip is essentially nature's most dangerous water slide. As the rock gets weathered and loosened,
entire slabs and blocks will just slide down the angled bedding planes right into the ocean, resulting in severe mass movements, like landslides. But what's really fascinating is that when the layers dip inland or landward, they actually lock together. Gravity is pulling the rock layers back into the earth rather than towards the sea margin. This structural arrangement produces incredibly stable, steep cliffs that are way more resistant to those massive landslides. Finally, Section 5, the sediment cell system. Let's pull all of this micro and macro geology together and look at the entire coastal landscape system as a whole. A coastline basically functions as a sediment cell. You can think of this as a largely closed loop of energy and materials operating within a specific boundary. You've got inputs of sediment, processes and flows moving that material around, stores where sediment accumulate like beaches, and eventually outputs. Honestly, it's a lot like a bank account. If erosion deposits a ton of sand into the system, the beaches grow. If severe storms make massive withdrawals, the beach shrinks. And the geology we've just been talking about, that is exactly what dictates the behavior of this entire financial system of sand and rock.
So here is a hinge question for you. Does weak lithology increase or decrease sediment supply to the nearshore zone? As you might guess, it heavily increases it, because weak rocks like clay erode so rapidly and suffer from constant mass movements, they break down and dump massive amounts of material right into the ocean. That sediment enters the cell as a vital input, flowing through the system and literally building the geographical features further down the coast.
And when you get weak and strong lithology sitting right next to each other, you get what's called a discordant coastline. This is where alternating bands of rock run perpendicular to the sea. The result on the planform, which is just the shape of the coast from a map view, is super striking. The bands of weak lithology erode rapidly backward, forming these deep sweeping bays. Meanwhile, the strong lithology holds its ground, fiercely resisting erosion and jutting out into the ocean as dramatic headlands.
So, to wrap up this explainer, I want to leave you with this classic 8-mark geography prompt. Explain how geology determines the morphology of coastal landscape systems. Just think about the weak bonds of clay, the interlocking crystals of basalt, the terrifying slides of a seaward dip, and the massive sediment inputs fueling the coastal cell. Ultimately, it is the hidden, silent geology beneath your feet that dictates the coastlines of our future. So, what will your local coastline look like 100 years from now? The answer is already written in the rocks.